Thank you, Sheetal and Islam, for that wonderful talk. Hi, everybody. My name is Nana, and I'm a Senior Product Manager. And joining me today is Angel Pizarro, our Principal Developer Advocate. And today we're going to be talking about how to run large-scale compute-intensive workloads on Amazon EKS. We know that Kubernetes was designed to, and it excels at running microservices applications, such as e-commerce websites. But running large-scale compute-intensive workloads or batch workloads, such as ML training or molecular modeling simulations, are fundamentally different in a few ways. As I'm getting started here, I'm going to walk through a few of these differences. First, we see that microservices is generally available to respond to a request. Versus batch workloads, you can think of a job having a runtime, and it starts and has an endpoint. The endpoint might be resolved as a success or sometimes even failure. Second, we see that microservices expect a response time in milliseconds, versus batch workloads have runtime for jobs that can be resolved in minutes, hours, or sometimes even days if you can think of your ML training workflows. Third, we see that microservices replicate their application components across availability zones to achieve high availability as well as adequate response times. But this is not a core requirement for batch workloads. Batch jobs are generally bin packed onto larger instance types for better performance and price ratio. These jobs also need fast access to data sources that are generally stored in high-performance file systems. Customers tend to co-locate all of this in a single AZ or replicate the entire setup across different AZs or regions. Finally, we see that microservices and batch workloads differ in the way that they scale. Microservices have a somewhat predictable temporary increases or decreases, but it's all measured in a linear scale. Versus batch workloads, we see that customers first perform a proof of concept where they're tuning their parameters for a much larger analysis. The scale between the proof of concept and the production run can be exponential. Finally, we see that customers only perform the production analysis maybe once. They're analyzing all the data that they've collected so far. Or even if it is repeated, it's rather infrequent, maybe on a monthly or quarterly cadence. Speaking of extreme scaling, here is an example of one of our customers. They ran 20K molecular modeling simulations and launched about 4,500 instances across 6 different AWS regions, which is the color gradations that you can see here. From there, they scaled down to a much lower number of instances for months to come. This is an example of one of the scaling requirements for batch workloads. There are a few more requirements here that I'm going to walk through next. Like I previously mentioned, batch workloads need to run to succession. That means that the scheduler needs to keep track of it over its job lifecycle. That means when it's being placed onto a compute resource, it needs to be tracked, versus if it needs to be restarted due to a spot or a hardware failure as well. We also see that a single batch job is generally a part of a much larger analysis. And so the scheduler would need to keep track of the dependencies between each of these. A lot of times we see jobs to be run as a workflow where the output of one of these jobs are fed into as an input for a later stage. In case of a failure early on in the analysis, it doesn't make sense to provision resources for the later stages. We should be automatically marking them as failed and moving on. Given the specific set of requirements for batch workloads, we do see that there are a few open source solutions out there, such as Unicorn, Volcano, or Q. Customers also have an option to roll their own solution using a general purpose scheduler, such as Carpenter, or using the Kubernetes Jobs API. While these solutions do have scheduling and scaling capabilities for Kubernetes, we've heard from customers that they've struggled to implement batch processes. And most of the open source solutions out there are customer managed, and scaling compute resources up and down in a cost-effective manner is time-consuming and challenging. Moreover, scheduling, prioritization, and placement of jobs in a quick and efficient manner is not easy. Most homegrown solutions have a high level of effort to optimize and maintain in the long run. We at AWS Batch have been solving these problems for a different orchestration called Elastic Container Service for over 5 years, and we're happy to announce that we're releasing support for EKS. We now provide a fully managed service for batch workloads, delivering on high throughput, scalability, and cost. Some of you might not be familiar with Batch, so let me dive deep into what is AWS Batch. It's a simple service that streamlines running workloads on the cloud. Batch is a scheduler that can control and run high-volume batch jobs as resources permit. It can also deliver all jobs as long as all dependencies on other jobs have been met. It's a resource orchestrator that can decide when, where, and how jobs are placed onto a job queue, managing complex workflow dependencies between them, where each stages can need a different mix of hardware, software, and storage requirements. Given this brief introduction on Batch, I want to discuss more on how to get started with it. You create and you provide these 4 resources, starting with a job, which is a single source of execution, which captures all your requirements and then refers back to the job definition. The job definition is like a blueprint or template for a job or jobs that you'd like to run. It tells us the application that you'd like to run, the role that you'd like to associate with when it executes, and the mount points to access the data that it needs when it runs. Customers can quickly instantiate a job given a job definition. They can also override one or more of these parameters when a job is submitted. As a job is being submitted, it's placed onto a queue while it's waiting for its turn. One of the first steps that a DevOps engineer or an admin takes is to set up the 4th piece of this, which is the compute environment. It's essentially a resource pool that decides whether you're using on-demand or spot instances. You can also pick specific instance families or instance types to stick to within your compute environment. The compute environment is where your jobs are run, and AWS Batch now supports 3 major platforms of compute: ECS, Fargate, and now releasing support for EKS. Next, I'm going to turn it over to Angel to talk more about the EKS integration.
Thank you. Oh, yes, the pointer. Let's dive in a little bit into these details, how this actually works. Like Nana had mentioned, the compute environment is where the action happens. This is where you're going to stand up the compute resources after you've defined the job. So imagine you have here on the slide, you see that you have an EKS cluster. That cluster has its managed resources as well as a regular auto-scale group running other applications within your Kubernetes cluster. Then you have a data scientist, maybe a machine learning application engineer who's looking to deploy an analysis on top of your clusters. So what you do as an administrator is set up AWS Batch with a job queue and a compute environment that is connected to the management plane, so the Kube API server. I'll talk a little bit in a further slide about the specifics of how you do this, but take it as given, this is the first step. Once the scientist starts submitting jobs, which you'll remember are pointing to particular job definitions, into the queue, what AWS Batch will do is if an autoscale group, batch managed autoscale group isn't defined already within your environment, it'll go ahead and create that and then start launching EC2 instances within that autoscale group. These EC2 instances are pre-configured to connect to your Kubernetes cluster. So kubelet will start doing its thing, saying, hey, I'm a new node, I'm in this batch namespace. One thing I'll point out here is that these resources are running separate from other auto-scaling resources in your environment. And these instances are not being mixed with other workloads within that clustered environment. So the Kubernetes scheduler sees it has a new instance. If it has defined daemon sets that can go on that instance, it'll go ahead and place them. Batch is constantly monitoring and watching the resources that it's added to the cluster. So when that node is ready, it'll start placing the jobs. And in this case, these are translated from the job definition into a pod spec and placing those pods directly on the instances that it has launched. And again, batch is not placing any pods or pod specs on other resources in that cluster. And I'll get to sort of the philosophy of why in a second. And so on and so forth. If you've got some really large models, you're going to fill up as much to the maximum capacity that you've defined in that compute environment. So, a couple things to point out. Batch is the main entry point for batch workload requests, right? We're not talking, you as the data scientists aren't talking to the Kubernetes structure directly, you're talking to the batch API endpoint. And that is inclusive of applications for instance, if you're using a workflow management system like Metaflow that already has support for batch, it should be relatively simple to translate from what is happening today with batch to go into your EKS clusters instead with very little changes, if any, are necessary. The second is that batch was launching worker nodes based on the jobs that it sees are queued, right? So as far as Kubernetes scheduler is concerned, it actually doesn't know about what's in the job queue at this time. Batch is acting as the coordinator, scheduler, and the queuing system to handle the full life cycle of the jobs that are being submitted in. And I'll call back to what Nena said, is because a lot of times the characteristics of jobs that have a definitive endpoint, a average runtime of minutes, might be days sometimes, and have some complicated retry strategies based on the underlying resources, are just different than microservices architecture. So Batch believes wholeheartedly when it knows what are the full set of workloads coming into it, it can make smarter decisions about scaling the resources that are needed for it and placing those jobs directly on the resources that it goes. So in point of fact, we're actually, as I mentioned, a completely separate part of that EKS cluster in terms of the resources, the compute environment that's going on. And this is by design. We are optimizing for cost and performance for batch workloads, and we feel that is best when the workloads aren't mixed, and then going back to other constraints that we've said that are related back to those batch workloads. And like I said before, batch is handling the pod placement. Today, we do this by a lot of labels and taints on the resources, as well as the pod spec, so that when we place a request for the Kubernetes scheduler, it's essentially bypassing almost all of scheduling logic. It's just essentially a record that says place this pod here within its CD, right? And then finally, one thing about batch that you're going to get, and Nathan had alluded to it earlier, you can actually have multiple compute environments attached to the same job queue. You can have different job queues. For instance, if you have resources specific to GPU clusters or other accelerators or other resources that are specific to that cluster, they could be a separate job queue. But those separate compute environments in that job queue will start filling up. In this case, we have an example where you might have an on-demand fleet that is there to guarantee some service level agreement for return of results in the initial case, but you want an optimistic spot fleet to launch to take care of the queue as fast as possible if the workload is scaling beyond a certain point, right? But these compute environments could be part of the same cluster. They could be part of actual different Kubernetes clusters. It's up to you. Right. Let's move on. So let's look at a couple of specifics here. So as I mentioned before, you define a compute environment using our API. This is a shot of the API. We support any version 1.20 plus. We actually recommend 1.22 because during some of our load testing, we think that 1.22 provides slightly better performance with respect to the kube scheduler and what batch is placing on there. So you'll get slightly better pod placement performance with 1.22 plus. And you can talk to the dev teams about that specifically, but we support anything above 1.20. And we're going to follow the support model of EKS. So the versions that EKS, the service, supports are the versions that batch will support as well. So the what I mentioned, how you define what a compute environment sees in terms of the EKS cluster, it's incredibly simple. It's essentially, let me get a laser pointer here so you guys can see, a couple of lines that say, here's my cluster endpoint and the Kubernetes namespace in which to launch nodes, right? So when the cluster is registered, so you predefine a namespace within your cluster for batch to launch processes. Right. From the job definition standpoint, we have an extra set of parameters that are specific to pod spec. This is fairly close to what the pod spec is today. It's a little bit opinionated because we feel that not everything in a pod spec applies to jobs, as in the sense of a job that is a job that is being scheduled from a batch computing standpoint, workload standpoint. We take this specification and then translate it into the pod spec with the proper labels and other features that will help Kubernetes place that pod onto the right instance. And then finally, I had mentioned daemon sets are just applied into the cluster. If you have daemon sets that you want to be specific to what's going on in the batch nodes that are bootstrapped and not other nodes in your clusters, you can do that through the mechanism you would expect with tolerations and taints. Right. So the shared responsibility model. This is where it really gets into how services integrate when there is a customer managed deployments, when there's AWS managed deployments like the EKS management plane versus the things that you do on the Kubernetes land. And then you have fully managed services like AWS, which is a scheduler and resource allocator at the top. There's a shared responsibility model there, right? So we need a few permissions defined, and what this boils down to is an OIDC provider, role-based access, a namespace that you predefine, and then creating that service account. As Nathan mentioned earlier, as the EKS service improves on the complexity and makes it simpler to add these things and more robust features, our team will adopt those. But as far as we're concerned, we actually just, we're following the same model other AWS services or any other interaction that you want with that Kubernetes cluster is service account, role-based access as far as in terms of Kubernetes and the mapping between the two. And finally, what happens over drift, right? Because we're running the services and you're running Kubernetes, you might do things to the configuration like update the cluster, update the nodes to different Kubernetes versions so you could take advantage either of new API changes or security patches or whatnot. Basically what's happening is that the compute environments are validating that the cluster it's talking to is what it expects it to be. Do I have the right permissions? Are you the right API version so that I'm making the correct calls? When drift happens, for either you've changed an IAM role through some git oops, the CE will first validate whether it can place jobs, and if it can't, or place nodes onto that namespace, and if it can't, it'll mark the CE as invalid, and the job queue will stop sending jobs into that compute environment for execution, right? It'll stop pulling from the queue. Once you fix whatever the invalid state is from the message, whether it's a new Kubernetes version, the CE will check again whether it's valid or not, and then mark it as valid once it gets over the hump. So in our example of updating the Kubernetes cluster, you would update the Kubernetes cluster to a new version, and then do an update to the compute environment to say, hey, compute environment, this is the new version of the Kubernetes cluster, and then it'll go back to valid state after it's done its validation. So shared responsibility. So why would you want to leverage AWS Batch for EKS workloads? Calling back to Nana's point about the reducing your operational overhead, right? The current state of technology and services and applications for batch workloads are predominantly deployed within your own your own environment. You're managing the queue, you're managing the resources, the spot market, the job retries, trying to optimize the throughput that you're putting on your cluster. As a managed service, we handle a lot of that for you. And we think that you'll really benefit from improved operations and cost optimizations as the telemetry team, the scheduling team that is looking at our managed services are being developed. Quick example of a feature that we developed that we didn't make much hay for, but it resulted in immediate cost savings for customers, is that we made a change in the scheduling and placement algorithm for when you have a large queue, you place jobs as fast as possible because you have a lot of fleet. And as soon as slots open up, you just start placing jobs. As you get to the tail end of that queue, though, you actually want to pack jobs on a smaller set of instances so that the instances that free up resources can actually shut down. Right? If you still place jobs, so it's essentially switching how we place jobs to not place jobs as fast as possible at the tail end, but it allows your fleet to scale down faster. So you take a small hit in the total runtime of the job, but you have a huge win in terms of cost savings because you've scaled down that fleet efficiently, a lot more efficiently, right? So those are the sort of examples that our team develops over time. We are constantly looking at the throughput rate. We work with the EKS organization to say what's the maximal cluster sizes and transactions per second for placing pods that we can do, and how can we get the defaults of EKS to better support high-scale workloads. All right. And then finally, advanced. So we've been sort of granular about jobs, right? But there's this whole other organizational structure to supporting data scientists and batch workloads. And one of those things are things like fair share scheduling. If you've got multiple groups accessing your resources, there's going to be resource contention. Even though there's a lot of hardware that we own within a region, you may have a budget. Right? You likely have a budget, and you need to account for a lot of different departments to fit within that budget. So fair share scheduling will allow you to tag jobs with either a project or departmental, and allow when the resource isn't, so you have a ceiling on the resource, when the resource isn't being subscribed by any other groups, they can take the whole thing. But as soon as jobs start coming in from other groups and other tags, it'll start deallocating resources from those groups, or not scheduling those as many, and sharing the total amount across those groups. So there's a lot of pretty cool features that we released with fair share scheduling. You can have that now with your EKS clusters. As we mentioned, job dependencies are a thing. You may want that within your execution system like Batch has, or you may want to offload that a bit higher level to a workflow management system, but it's there. And then other compute allocation strategies, whether you want the exact fit of the instance that you need, or you can take from a set of instance families, or you can have spot optimize across AZs. So there's a bunch of allocation strategies that Batch supports today that you get out of the box. And then finally, integration with other AWS services. Since it's the API endpoint, you can today directly interface Batch with EKS with step functions, event bridge, and then use IAM to interface with other resources. On the Kubernetes side, why would you want to use Kubernetes with Batch? One, you really want to take advantage of Kubernetes, the ecosystem, the partners, the tools. One example would be monitoring and visualization with Prometheus and Grafana. Another one would be to use kube costs to see what costs are going in particular jobs and schedules. I'm not going to show an example of this today, but we have a booth session tomorrow where we have a whole hour with one of the engineers. If you're really interested, you can poke them for a lot more details, and they'll show you an example of how we, just a quick example of when we were doing our scale testing, placing 10,000 nodes over time, 10,000 pods over time, and you can see them being placed on the cluster at what rate. So it's pretty cool. Come join us, come ask questions. Happy to be here. Thanks.